Magnetism is one of the most fascinating and fundamental forces in our universe. Today, we'll explore what magnetic forces are and how they work around us every day. Magnetic forces are one of the four fundamental forces of nature, alongside gravity, the strong nuclear force, and the weak nuclear force. These forces govern all interactions in the universe. Magnetism is actually part of the electromagnetic force, which also includes electric forces. These two phenomena are closely related and together form one unified force. Let's observe magnetic forces using two simple bar magnets. Each magnet has two poles, a north pole marked N and a south pole marked S. When we bring opposite poles together, north and south, they attract each other with a magnetic force. This attraction pulls the magnets toward one another. However, when we bring like poles together, two north poles or two south poles, they repel each other. The magnetic force pushes them apart. A magnetic field is the invisible area of influence around a magnet where magnetic forces can be detected. Think of it as the magnet's sphere of influence. We can visualize magnetic fields using field lines. These imaginary lines show the direction and strength of the magnetic force at different points around the magnet. Our planet Earth is actually a giant magnet with its own magnetic field. This field extends far into space and protects us from harmful solar radiation. Earth's magnetic field is what makes compasses work. The compass needle, which is a small magnet, aligns itself with Earth's magnetic field lines, always pointing toward magnetic north. Understanding magnetic forces and fields is fundamental to grasping how many technologies work, from electric motors to MRI machines. In the following sections, we'll explore these concepts in greater detail. Magnetic fields don't just appear from nowhere. They are created by moving electric charges. Understanding this fundamental principle helps us explain everything from electromagnets to permanent magnets. The simplest example is a current-carrying wire. When electric current flows through a wire, it creates a circular magnetic field around the wire. The direction of this field follows the right-hand rule. Around this current-carrying wire, circular magnetic field lines form. These invisible field lines show the direction and strength of the magnetic field at different points around the wire. But where does this magnetic field actually come from? We need to look deeper, at the atomic level. Inside every atom, electrons are constantly moving around the nucleus, and this movement creates tiny magnetic fields. As the electron moves in its orbit, it acts like a tiny current loop, creating a small magnetic field around the atom. This is called an atomic magnetic dipole. In most materials, these atomic magnetic fields point in random directions and cancel each other out. However, in permanent magnets, something special happens. The atomic magnetic fields align with each other. When atomic magnetic fields align, they add together to create a much stronger, noticeable magnetic field. This is how permanent magnets get their magnetic properties, from the coordinated alignment of countless tiny atomic magnetic dipoles. Magnetic fields are invisible forces that surround magnets, but we can visualize them using magnetic field lines. These imaginary lines help us understand both the direction and strength of magnetic forces. Let's start with a simple bar magnet. Every magnet has two poles, a north pole shown in red and a south pole shown in blue. Magnetic field lines are imaginary lines that show the direction of the magnetic force. These lines always flow from the north pole to the south pole of a magnet, creating curved paths through space. Notice how all the field lines point from the north pole to the south pole. This direction represents the path that a small north pole would follow if placed in the magnetic field. Different magnet shapes create different field line patterns. In a horseshoe magnet, the north and south poles face each other, creating strong, straight field lines between them. The spacing between field lines tells us about the strength of the magnetic field. Where field lines are closer together, the magnetic field is stronger. Where they are farther apart, the field is weaker. We can actually see magnetic field lines in real life using iron filings. When iron filings are sprinkled around a magnet, they act like tiny compass needles and align themselves with the magnetic field. Watch as the iron filings align themselves with the invisible magnetic field lines, revealing the beautiful curved patterns that we've been drawing. This demonstrates that magnetic field lines represent real physical forces in space. Magnetic field lines are powerful tools that help us visualize and understand invisible magnetic forces. They show us direction, strength, and the beautiful patterns that magnetic fields create in space around us. When electric charges move through a magnetic field, they experience a force that can change their direction of motion. This magnetic force is one of the fundamental interactions in electromagnetism. Consider a positive charge moving with velocity v through a magnetic field B that points into the page. The magnetic field is represented by these cross symbols, indicating field lines going away from us. The key property of magnetic force is that it acts perpendicular to both the velocity of the charge and the magnetic field direction. In this case, the force points upward, perpendicular to the rightward velocity and the magnetic field pointing into the page. To determine the direction of magnetic force, we use the right-hand rule. This is a simple method that helps us visualize the three-dimensional relationship between velocity, magnetic field, and force. First, point your thumb in the direction of the charge's velocity. Then, point your fingers in the direction of the magnetic field. Finally, your palm will point in the direction of the magnetic force on a positive charge. Now let's see what happens when a charged particle enters a magnetic field. The particle initially moves in a straight line, but once it enters the magnetic field region, the perpendicular force causes it to follow a curved path. As the particle moves through the magnetic field, it follows a curved trajectory. The magnetic force continuously acts perpendicular to the particle's velocity, causing it to move in a circular arc while inside the field region. The magnitude of the magnetic force is given by the formula F equals qvb sine theta, where q is the charge, v is the velocity, b is the magnetic field strength, and theta is the angle between the velocity and magnetic field vectors. This magnetic force on moving charges is fundamental to many technologies, from particle accelerators to electric motors, and helps us understand how charged particles behave in magnetic environments. Current flowing through a wire is simply moving electric charges. Since we know that moving charges experience forces in magnetic fields, it follows that current-carrying wires must also experience magnetic forces. Consider a straight wire carrying current I. The current flows in one direction through the wire, representing the movement of electric charges. Now we place this current-carrying wire in a uniform magnetic field. Here, the magnetic field points into the page, which we represent with X symbols. The wire experiences a magnetic force perpendicular to both the current direction and the magnetic field. This force acts on the entire length of the wire. The magnitude of this magnetic force depends on four key factors: the magnetic field strength, the current, the length of the wire, and the angle between the wire and the magnetic field. The formula for magnetic force on a current-carrying wire is F equals BIL sine theta, where F is the force, B is the magnetic field strength, I is the current, L is the length of wire, and theta is the angle between the wire and magnetic field. To determine the direction of the magnetic force, we use the right-hand rule. Point your fingers in the direction of current, curl them toward the magnetic field direction, and your thumb points in the direction of the force. This principle of magnetic force on current-carrying wires is fundamental to the operation of electric motors, where the interaction between current and magnetic fields creates rotational motion. Electromagnets represent one of the most practical applications of the relationship between electricity and magnetism. Unlike permanent magnets, electromagnets can be turned on and off, and their strength can be precisely controlled. An electromagnet is created when electric current flows through a coil of wire. The moving electric charges generate a magnetic field around the coil, effectively turning the coil into a magnet. When current flows through the coil, magnetic field lines form around it, just like around a permanent magnet. The coil now has a north and south pole and can attract magnetic materials. Adding an iron core dramatically increases the electromagnet's strength. The iron becomes magnetized and amplifies the magnetic field created by the current in the coil. The strength of an electromagnet can be controlled in two main ways. First, by increasing the electric current flowing through the coil. Second, by increasing the number of turns or loops in the wire coil. Electromagnets have countless practical applications. In junkyards, powerful electromagnets lift and move heavy metal objects, The electromagnet can be turned off to release the metal exactly where needed. In medical applications, MRI machines use extremely powerful electromagnets to create detailed images of the inside of the human body. These electromagnets must be precisely controlled to generate the magnetic fields needed for imaging. Electromagnets demonstrate the practical power of controlling magnetism with electricity. By simply turning current on or off and adjusting its strength, we can create magnets that work exactly when and how we need them. Earth possesses a powerful magnetic field that acts as an invisible shield, protecting all life on our planet from harmful solar radiation and charged particles streaming from the sun. Earth behaves like a giant magnet with magnetic field lines extending far into space. These field lines form a protective bubble around our planet, with magnetic north and south poles similar to a bar magnet. Earth's magnetic field is generated deep within our planet's core. The Earth consists of several layers: a thin outer crust, a thick rocky mantle, and a two-part metallic core. The key to Earth's magnetism lies in the outer core, which contains molten iron and nickel at temperatures exceeding 4,000 degrees Celsius. As Earth rotates, this liquid metal moves in complex patterns, creating electric currents that generate our planet's magnetic field. The sun constantly emits a stream of charged particles called solar wind. Without Earth's magnetic field, this high-energy radiation would strip away our atmosphere and make life impossible. Earth's magnetic field deflects most of these charged particles, bending their paths around our planet. The magnetosphere acts like an invisible shield, redirecting the solar wind and protecting our atmosphere. While most solar particles are deflected, some do enter Earth's atmosphere near the magnetic poles. When these charged particles collide with gases in our upper atmosphere, they create the beautiful phenomenon we know as auroras, the northern and southern lights. Earth's magnetic field is truly our protective shield, generated by the dynamic motion of molten iron in our planet's core. It deflects harmful solar radiation, preserves our atmosphere, and creates the spectacular auroras that remind us of this invisible but vital force protecting all life on Earth. Magnetic forces and fields are not just abstract scientific concepts. They power countless technologies that shape our modern world. From the motors in our appliances to the trains that transport us, magnetism is everywhere around us. Electric motors convert electrical energy into mechanical motion using magnetic forces. When current flows through a coil placed in a magnetic field, the magnetic force causes the coil to rotate continuously. Generators work in reverse to motors. When a coil moves through a magnetic field, it generates electrical current. This is how power plants convert mechanical energy from turbines into the electricity that powers our homes. MRI machines use extremely powerful magnetic fields to create detailed images of the inside of the human body. The magnetic field aligns hydrogen atoms in our bodies, and radio waves cause them to emit signals that create medical images. Magnetic levitation trains use powerful electromagnets to both lift the train above the track and propel it forward. Without friction from wheels, these trains can reach incredible speeds while providing a smooth, quiet ride. The humble compass demonstrates one of the most practical applications of magnetism. A magnetized needle naturally aligns with Earth's magnetic field, always pointing toward magnetic north and enabling navigation across the globe. From the motors in your smartphone to the generators in power plants, from medical imaging to high-speed transportation, magnetic forces and fields are fundamental to modern technology. Understanding magnetism helps us appreciate the invisible forces that power our world. Take a moment to look around you and discover the many ways magnetism influences your daily life. From the speakers in your headphones to the hard drive in your computer, magnetic forces are working behind the scenes to make modern life possible.